Okay, so let me continue. And this part will be about the exercises. Basically, I will do a live demo, right? And you can follow me. So we provided you with a Git repository. And in this Git repository, you can get the scripts that are using and all the files. So basically here, you need to clone the repositories. And I will do now, I will follow these instructions here. I will move to the directory Proi, no backup, QMM 2021. This is the folder or the project storage that we set up for this course. So if you write something on this project folder and you want to keep it, then you should back up in your local resources or in other project that it is yours at HPC2M. And that's because at some point we need to release this space, and then you haven't removed your data, then you will be notified and for removing the data that you have stored here. So this storage is just for the course. So once you are here, you can clone the repository. Says that I make a mistake. Oh, I see. Oh, I forgot to, sorry for that. I need to make a repository, a username repository, or a username folder. Because if you don't create your own folder, then you will have the course QMM folder, and all the others could modify your course QMM folder. That's why I ask you this step to create your own folder with your username, for instance, or any other name that you like. Then I will go to the folder that I created, in this case with my username. And after that, I will clone the repository for the Git course, right? And here, once I am in my own username folder, I will move to course QMM, right? This is the README file that you are watching here in the web browser. These are the lectures, and these are the folders for the exercises. So let me go to the first exercise, which will be on ORCA and MD and NAMD. I go to view codes and NAMD. Okay, the first step is to load the modules. First of all, I will do a best practice, which is a purge the modules that I have loaded before, and I do that with this command here. And then I will load the modules for VMD. Now I will move to the folder for Orca. Here you can find the following files. This is a file for the topology and parameters for GTP, small molecule. The README file that you are watching here on the web browser, and the two batch script that we will use later on. So here we assume that you are here in this folder where I'm sitting currently. And now I will open a VMD, and this is done after loading the modules by typing VMD. So unfortunately, the text of this window is quite small, right? And I will try to be slow in this part because maybe you cannot see what I'm seeing here. It says go to extensions. I will go to this part and then simulation and use QwikMD. So one feature of VMD, as you can see, is that it has many tools, right? Including, for instance, setting up the simulation, manipulating the structure. So it's a nice suite for getting started with molecular dynamics, and also for more advanced setups. So in the present case, we will use the QwikMD. And here you see, I have two questions. Okay. You see the window for QwikMD, and then if I put here a comment, if this is the first time that that you open the QwikMD, then it will ask you if you need to create the folder, and you can accept that. In this case, if you see your home directory after clicking OK, you will see two files. I will show you. You will see the QwikMDs. QwikMD-RC, where you will save all the options for QwikMD. In particular, in my case, it looks like this. It is for the setting of environment variables that I did before. And also you will get a QwikMD folder. Let me see. A QwikMD folder, and here now VMD will save several files, including, for instance, the parameters and so on. Some files that are required for QwikMD. Okay, now let me go to this box here. So in the browser option of QwikMD, which means here, I will type Q1 QRA, which is the protein, the PDB ID of this protein, and then I would load the protein. So notice that here I'm using one setup, modified setup from the NAMD tutorial from QwikMD, right? You will realize about that if you take a look at the NAMD tutorials. And I also added some features to this system. So here we get a message which says that there were some renamings for the atoms in the simulation according to the CHARM 36 topologies. So I will accept that, right? And because I set it up, the parameters previously for GTP, I won't get any message, right, from QwikMD saying that the parameters are missing, right? But if this is the first time you do it, you can accept that part as well. And we will deal with the parameters later on. So once we have loaded the Q1 molecule, then we go to chain type and selection. And we will disable or deselect this A and water option. So I will click on this because we don't want, I don't want the water molecules that are present in this structure. And then we can go to structure in manipulation check. And here is the point. So in my case, because I have already added the parameters, then this square looks green, but in your case, it should be red. So let me go and do it just for the beginning, because I need to show you how to do that. I will remove, or better, I will back up my QwikMD MC file. Okay, now that I remove these QwikMD folders, then it will see the QwikMD setup as if I were just starting. So I will open my QwikMD. And this is the window that it shows me that I need to create some directory and some configuration file for QwikMD. I will say, okay. So now the folders and the QwikMD RC file have been created. I will open or load again the protein. And this is the box for the renaming of the atoms. And this is the additional message which says that some parameters are missing, and I need to do an structure and manipulation checking. So I will just say okay. Yeah. Then in chain selection, I will click on this option to disable the waters, right? Then go to check and manipulation. And now because QwikMD doesn't recognize the parameters, it shows me that this square is red, and I cannot proceed unless I change the parameters or I add the parameters. So let me go to topologies and parameters. I will click on this, and this tells me that in particular, the residue 167 of chain A is unknown, and this corresponds to the GTP molecule. Then I can go to add topology, and then I will click on this symbol here. So one thing here is that we need to change the path where we are sitting, because as you see here, QwikMD recognizes this installation folder to load the parameters for the protein. But in our case, we need to move to the folder where this file topar all36str is located. And in particular, this is our current folder. So I know that this folder should be Pro no backup. And then the folder that we set and my username, right? And I will try this first. So now I can see the folder course QMM. Then I can click on that and go to Orca. And here is the file that I need to open. So notice that the username should be your username or the name that you set for the folder, right? Otherwise, QwikMD will recognize this most probably as the folder where you are working, and then you will try to open the files that I'm creating. So open the file, right? And then you can see here several options. Then we can go to the GTP molecule, which is the one that we are interested in. And we will use here hetero options, right? And once we do that, we will apply the changes. And QwikMD says that some parameters will be added to the library. And if you want the changes, then I will say yes. And it suggests to restart QwikMD. So I will do that. Okay. So I will close all the windows that QwikMD used. And then after closing, I will go again to QwikMD. And here I will load the protein again. So it shows me again the message for the renaming of the atoms, and I say, okay. But now the message related to the parameter is not displayed, which means that the parameters for GTP have been recognized. So if you go to check a manipulation, you should see this square as green, right? So then again, we disable the waters. And in this case, I don't want the waters in the protein. If you want that, you can leave it there. It depends on you. But for this setup, I suggest to disable that. And then you can see only the protein and also the GTP. So now in QwikMD, you can start with the setup and go to the option called advanced window, advanced run. And here, first, we will try a MD simulation, right? So choose the solvent explicit, which means that the waters will be modified with the sticks and balls model, as I showed you before. The other option could be implicit model, where the water is modeled just like a continuous media, right? This will be explicit, then a minimal box. I will click on this. And the buffer, I will use a 12 angstroms buffer. The concentration of salt, this one, and the salt is sodium chloride. Yeah, but you can also use another type of salt. But in this case, I'm using sodium chloride. Now in the protocol, let me go and change these steps. You can modify the number of steps because, as you can see here, this is a short course. For a realistic simulation, equilibration is a very important part, and you need to try the very long simulation in some cases. But for the purpose of this course, I will reduce these steps, and I will change annealing to 1200. So I click on this number here, and when it appears this window, I will change that to 1200. Equilibration, I will set it to 5,000, 50,000. And finally, I will remove this step here. This is the production step, but in this particular case, I will remove that. Again, just for the purpose of teaching today. Then I can go ahead and click on this, remove, right? And now I will close this window. And then in the simulation setup, here, I will start saving the files. So I will click on save. And this is the file that will be created. And in particular, this is a folder, and this will contain all the relevant scripts that are needed for the classical molecular dynamics simulation. So be aware of this path. So if for some reason you are using an incorrect path here, you will be saving the files in the folder of other person. In particular, in my case, if you remember, I used the username, but you can also be using the name that you choose. So check this path at this point, right? And then I will save the option here, right? And finally, here I will click on prepare all the required files. So VMD is doing some stuff here. And finally, once I created the files, I can close VMD. Right? So now you can see that some files appeared in your directory. In my case, this is this path, but of course you should be using your own copy. So this file called MDSim, QwikMD, contains the configurations for QwikMD for this particular run, right? This looks a bit crowded, but this is how the QwikMD reads the instructions, right? And the folder that we'll be using is called MDSim, right? So I will ask you to copy the first file called namd.sh, and this is done with the cp command namd.sh, and then I will go to mdsim and run. So with this step, I will be copying the script that I had at the beginning into this folder here. And then I will move to the mdsim run folder. And after that, the namd.sh file should be here, right? So what is the scheme that I am doing here? I'm using basically VMD and the particular QwikMD plugin to set up the simulation. And now that we have all the files for running the MD simulation, then we can use the batch queue, right? If you, for some reason, have your NAMD and VMD set up in your local machine, then it will be straightforward for you to run your simulation by using the QwikMD toolbox, right? Just click on run the simulation, and then it will use the NAMD executable in your local machine. But we cannot do that because here in HPC2N, because we work with a batch system, which is better, or it's better suited for dealing with many users, right? So that's why here I am using just QwikMD for setting up, and then we will be running with the batch queue. And that's why we need the namd.sh file. So let me open some file from QwikMD. In particular, the first step, which is the minimization. And here you can see some options like the cutoff distance, the particle mesh equal summation for electrostatics, which is set to on. And then where the coordinates are written, are read for this simulation. And NAMD also needs the PFS file, which is automatically generated by QwikMD. Some temperature options, harmonic constraints at the beginning, because when you get the structure from the crystal structure and you apply a minimization, there could be some big changes in the structure, and that's why it's recommended to use some constraint at the beginning in the minimization and equilibration parts. And here is some outputting for the files, including the trajectory, which is called minimization.dcd. Some options for restarting, and this is good. And this option is offered by most, if not by all, the packages. And in this case, you write some restarting files or checkpoint files in some software is called like that. And then if you want to continue the simulation to get a longer sampling, then you can use these restart files to continue the simulation.
There is a question on the Q&A document.
Let me see.
Can we use QwikMD to set up the MD simulation in another program like Gromex, for instance?
No. This is what you can do is that you can get the resulting PDB file and do some transformation, but that should be manual, right? For that reason, sometimes I use the Charm GUI interface. I don't know if you are aware of that. So previously you didn't need to log in, but now they are asking for an account. So I can copy and paste. In the chat. So in case you don't know that, but this is very well known. And in this case, you can start with a crystal structure, a PDB file, and then at the end you will get the files in the format of different software like an NAMD, Gromex, Genesis, and so OpenMM as well, right? So this is a good option, and I would suggest that to explore, right? But I will not cover this. This is quite good, right? Especially for larger systems like membranes or the COVID-19, as you can see here. So it makes some good processing. But in this case, you will generate a PSF file, which is recognized for in NAMD and also in Charm. So actually, I am a Charm user, and the good point in Charm is that you can use many methods available for computational chemistry, and it's well integrated with NAMD. So if you obtain some files from Charm, you can use that in NAMD and vice versa with little transformation. And here, let me go ahead with this script. This is the thermostat and the varostat that I mentioned in my lecture, yes, for controlling the temperature and the pressure. In general, you don't need to change these parameters, but of course, you need to look at the literature and what parameters are used for the particular system. It strongly depends, for instance, on the pressure and volume, for instance. And this is the integrator parameter section. In this case, I'm using, or QwikMD is using by default 2 femtoseconds, right? And this is the frequency for updating the electrostatics, non-bonding interactions. And this is the section for the force field parameters. You see that QwikMD reads the parameters that we pass to it together with other parameters for lipids, carbohydrates, and so on. So this is not required. For instance, if you are not using carbohydrates, and you could see if you don't need that, but actually QwikMD reads all these parameters by default, but in general, it's not needed. And implicit solvent, this is off, so we are not using implicit solvent. And here, this is the number of steps that are used for the minimization. In this case, is 2000. So this is the case in the case that there exists a continuation. So once we have the configuration files, we get the minimization, the equilibration, and the annealing configuration files. Then we can go to the NAMD batch file, right? And you will see this instruction here for the batch queue. We will ask you to change the project ID to the one that we have for today, which is SNIC 2021-22 907, right? I think we have also a reservation. Do you have the name of the reservation, Brigitte? So we have a reservation, but I cannot see. But well, are you talking, Brigitte? I cannot hear you. Okay, well, I will set at this point just the project ID, which in principle will work. And once I have the reservation, I can add it to this script, yes, so that your jobs run faster. So that's basically how you will run. You will run the configuration file, minimization, annealing, and equilibration, right? So once you have this, then you can submit the job to the queue with sbatch namd.sh. And then you can check the job in the queue with the following command: sq -a-u and your username. In my case, is P Ojeda-May. So notice here that namd is running already, right? And I will use a command called job usage, which is available on the login node, and the job ID that I got upon submitting with sbatch. And this will give me a URL. I can copy this URL and paste that in my local browser. And here you will see the information for this job. I will reduce the updating frequency to 1 minute, for instance, and see what namd is doing. So it's still running. So here you started to see how namd is using the resources. So take a look at the namd sh file, and we requested 28 cores, and namd is using about 100% of these 28 cores. This is a useful tool to see if the resources that you requested are being used well, right? Sometimes, for instance, we forget to add the proper commands, and we request more resources than we are using actually, right? But in the present case, we requested 28, and we see that we are using around 100% of that. In addition to that, we can see the memory and other metrics for the Linux system. So we also get some output files from NumD, right? And we can check that with the tile minus F 400, M400, and this will update the display of the information when it is modified in the file. As you see, NumD is doing the computations, right? And when it finishes, we will get the trajectory, which is saved in the DCD file. Actually, we can start looking at the trajectory. So if we go to the instructions, we can see that if we type VMD and then MD, SEM, QwikMD.psf, and equilibration.bcd, then we will watch the trajectory. VMD needs a structure file. It could be a PDB or a PSF, and then the trajectory file, which is saved in this DCD file called equilibration. So here you can see the system, and it says that up to this point, NumD has computed 19 frames, right? I use some options called orthographic and diff queuing to avoid the projection. Then we can go to presentations, and I will monitor, for instance, the protein. And I will create a representation for res name GTP, for instance. And this, in this case, the drawing method will be licorice, for instance, with a bond radius of 0.1. And the proteins, I will display that with the new cartoon. Right? So this will look like this. Also, if you go to the extensions, you can see several analysis tools. In particular, we can choose the trajectory, RMSD trajectory tool. And for that, I will choose the backbone, right? And this will compute the RMSD, which is the root mean square deviation. And the reference tool, the reference molecule will be the top one. And the trajectory will start from the frame 0. I also want to display the plot. And I don't want to save the file, right? I just want to visualize how it looks. So then I will also use the backbone atoms for computing the alignment and the RMSD. By clicking on this, I will align all the frames in the trajectory. And then this button here will show you the RMSD, right? With respect to the first frame. So I can close this. And basically in molecular dynamics, in classical one, what you want to get is this motion of the atoms, from which all the properties or thermodynamical properties can be computed. Is there any questions at this point? So you can see that even for this short simulation, it's taking some time. So I did it before and it takes about 10 minutes to run. So you can leave your job in the queue. Any questions that you have? Any comments? Or do you want to speak, Mehdi, or because we are recording this part? If you want to speak, just
I want to speak. Can I speak? Okay. I have a question about the residues that have more than one protonation states, for example, histidine or glutamate. How do you deal with these residues?
So you say the protonation state.
Yeah, in setting up the MD simulations, how do you assign the protonation states of histidine, for example? It can be protonated on ND1, NE2, or on both the nitrogen atoms.
Yes, well, the protonation state can be set in the PDB file, right? And in particular for QwikMD, I haven't tried that, but the protonation state it should be already present. Let me show you. They should be present in the force field. For instance, if we go to some residue like arginine, chop. Let me see if it is here. Interesting. Well, the point is that the protonation it's already included in the parameters, and I will suggest for that to create your PDB, because in the present case you are loading the 1QRA molecule from the database, and if you have a specific protonation state, then you can start with the appropriate PDB file, right? And there should be another tool in VMD for doing the protonation state, but I will explore that and I will come back to you again.
Okay, thank you.
Yes. That's a good point about the charm GUI that I mentioned before, because in charm GUI you can specifically set the protonation state. Have you tried that? So let me see. Yeah. Well, if I have some words about charm GUI later on, I will let you know. So by now, it should have finished. As you can see here, I don't get any more statistics on the job. So it's a good tool to explore. And if I check again the queue, so the job is not running any longer. So in addition to this, we get this restart files for doing a continuation and so. Any questions? If not, maybe you can take a break now and we can come 11:05. So, and we can continue with the second example.